Pacific, 1944. A carrier deck was the most dangerous workplace in the war. 40 tons of steel launching into the sky every 2 minutes, fueled by rivers of aviation gasoline that could turn the entire ship into a floating inferno in seconds. But somewhere between chaos and catastrophe, foam became the thin line between survival and annihilation. The men who worked those decks knew the statistics. One spark near a fuel line, one aircraft crash on landing, one ruptured tank during combat operations. Any of these could kill dozens in moments and cripple a carrier for months. Fire was the silent enemy that lived inside every successful mission, waiting in every gallon of avgas, every hot engine, every worn hydraulic line. Yet among the sailors in oil-stained coveralls and the engineers sketching diagrams in cramped compartments below, a quiet revolution was unfolding. Foam, simple, suffocating, scientifically precise foam, was being tested, refined, and deployed across the fleet. It didn't look like much. It didn't roar like the guns or gleam like the aircraft, but it saved more lives than most weapons ever fired. This is the story of the men who turned chemistry into courage, who built systems under bombardment, and who learned that survival at sea depended not on firepower alone, but on the speed with which you could smother the flames before they devoured everything you loved. Before we continue, subscribe and turn on the bell. Here we tell real, untold stories of World War II, stories of innovation, sacrifice, and the fragile moments of survival that history almost forgot. Chapter 1. The Deck That Burned. The carrier deck stretched nearly 3 football fields long, but to the men working it, the space felt impossibly small. Every square foot was calculated, choreographed, timed to the second. Aircraft launched, aircraft landed, fuel lines snaked across steel plating, ordnance carts rolled between parked planes, and beneath it all, thousands of gallons of aviation gasoline waited in tanks just below their feet. The air smelled like exhaust and salt and oil. The noise was constant, propellers spinning, engines roaring, deck crews shouting over the wind, and somewhere in that mechanical ballet, everyone understood the same unspoken truth. One mistake, and the whole ship could burn. It had happened before. Carriers lost to internal fires, not from enemy torpedoes or bombs, but from fuel igniting during routine operations, a hard landing that ruptured a fuel tank, a damaged aircraft leaking gasoline across the deck, a spark from metal scraping metal. The stories circulated among the crew. Ships gutted from the inside, men trapped below decks, entire squadrons lost not to the enemy but to fire. The Navy's early attempts at fire suppression were crude. Water hoses, buckets of sand, firefighting teams in asbestos suits racing toward flames that moved faster than any man could run. Water worked on wood and paper, but gasoline floated. Sand smothered small fires, but large ones simply burned around it. And time. Time was the one resource no one had when fuel ignited on a flight deck. Sailors learned to watch the fuel handlers with a mix of respect and dread. Those men walked the deck with hoses in hand, pumping thousands of gallons into aircraft between sorties. One slip, one worn coupling, one moment of inattention. The consequences were immediate and absolute. Engineers below decks studied the problem with growing urgency. They analyzed burn patterns. They calculated fuel dispersal rates. They reviewed damage reports from ships that survived fires and autopsies from ships that didn't. The conclusion was clear. Water couldn't win this fight. Something else was needed. Something that could cover fuel faster than it could burn. Something that could deny oxygen to flames without adding weight or complexity to an already overloaded system. Foam had been tested in industrial applications, factories, refineries, chemical plants. But a carrier deck wasn't a factory floor. It pitched and rolled. It operated in salt air and tropical heat and Arctic cold. Equipment had to work in combat, under fire, with half-trained crews operating in chaos. Theory was one thing. Reality was something else entirely. The first foam systems installed on carriers were experimental. Nozzles mounted along the deck edges. Tanks of foam concentrate stored below. Activation protocols that required manual operation. The crews eyed the equipment with skepticism. It looked fragile. It looked complicated. And when seconds mattered, complicated meant deadly. But the engineers kept refining. They tested mixtures. They adjusted pressure. They trained crews on activation procedures until the movements became muscle memory. And they waited for the moment when theory would be tested by fire. That moment came on a morning in the Pacific, when a damaged fighter returning from a strike mission missed the arresting cables and skidded sideways across the deck, its ruptured fuel tank spraying gasoline in a wide arc. The pilot scrambled free, deck crews scattered, and for 3 seconds everyone on that ship held their breath, waiting for the spark that would turn fuel into flame. The spark came, and the fire followed. Chapter 2. The first ignition. The flames spread faster than thought. One moment, liquid gasoline pooling on steel. The next, a wall of fire racing across the deck, consuming air, metal, anything in its path. Men shouted. Alarms sounded. The carrier's loudspeaker crackled with orders that were already too late. Fire on the flight deck was every sailor's nightmare. It didn't matter how many drills you ran or how many times you rehearsed the procedures. When fuel ignited in open air, instinct took over. Some men ran toward the flames with extinguishers. Others ran away. A few stood frozen, staring at the inferno, calculating whether their ship would survive the next 60 seconds. The foam system operator was a young sailor from Ohio, barely 20 years old, trained on equipment he'd only seen activated once during a drill. His station was a panel mounted near the island superstructure, protected by a thin steel shield. He could see the fire spreading. He could hear the screams of men caught too close, and he could feel the heat radiating across the deck even from 30 yards away. His hands moved to the activation lever. The instructions were simple. Pull the lever, open the valves, flood the deck. But nothing about this moment felt simple. The system was untested in combat. The foam might not work. It might make things worse. And if he flooded the deck while aircraft were still landing, he could cause a crash that would kill more men than the fire. But the fire wasn't waiting for perfect conditions. It was feeding on fuel, growing, reaching toward parked aircraft loaded with ordnance. If those planes ignited, the explosions would gut the ship. He pulled the lever. The foam came in a rushing torrent, white and thick, pouring from nozzles mounted along the deck perimeter. It spread like a living thing, flowing over the flames, smothering them, denying them oxygen. The fire fought back, flaring, surging, trying to burn through the foam barrier. But the foam kept coming, relentless, mechanical, precise. Deck crews watched in disbelief. The flames that had seemed unstoppable moments before were shrinking, retreating, dying. The foam covered the spilled fuel, turning the deck into a white landscape that looked almost peaceful. The roar of fire gave way to the hiss of extinguishing heat. And then, silence. The sailor at the control panel didn't move. His hand was still on the lever. His breath came in short gasps. Around him, men were staring at the foam-covered deck, processing what had just happened. The fire was out. The ship was safe. And the system, the untested, experimental, seemingly fragile system, had worked. An officer approached, his face blackened with soot, his voice hoarse. He looked at the foam, then at the sailor, then back at the foam. He didn't say anything. He didn't need to. The evidence was spread across 50 yards of flight deck. But as the immediate crisis passed, questions surfaced. The foam had stopped the fire, but it had also created new problems. The deck was slippery, treacherous. Aircraft couldn't land until it was cleared. Cleanup crews would need hours to wash it away. And the foam concentrate tanks below were now half empty, with no resupply available for days. Engineers scrambled to assess the system's performance. They measured response time. They calculated foam coverage rates. They interviewed the operator, the firefighting teams, the pilots who had witnessed the event. The data was encouraging, but incomplete. One successful test didn't prove the system could handle every scenario, and scenarios were multiplying. Carriers operated around the clock. Fuel flowed continuously. Aircraft landed in all weather, in all conditions. The next fire could be larger, faster, more complex. The next operator might hesitate. The next malfunction might occur at the worst possible moment. The Navy's position was clear. Foam systems would be standardized across the fleet, but standardization required training, logistics, maintenance protocols. It required convincing crews that this new equipment was worth the deck space it consumed and the weight it added to an already overloaded ship. Some sailors embraced it, others remained skeptical, and everyone understood that the real test would come not in controlled conditions but in combat, when chaos ruled and seconds determined survival. Now tell us in the comments where you're watching from, and how far these forgotten stories of wartime innovation have reached. Your voice helps keep memory alive. Chapter 3. The Chemistry of Survival. Below the flight deck, in compartments lit by harsh fluorescent tubes and ventilated by rattling fans, Chemical engineers worked problems that couldn't be solved with guns or courage alone. Foam wasn't magic. It was science. Carefully balanced mixtures of surfactants, stabilizers, and water, designed to create a barrier between fuel and oxygen that could withstand heat, movement, and time. The challenge was creating a formula that worked in every condition a carrier might face. Tropical heat that made foam collapse too quickly, Arctic cold that turned it sluggish, salt spray that degraded chemical bonds, rough seas that made precise application nearly impossible, and always the pressure of time, because fuel fires didn't wait for ideal circumstances. Early foam formulas failed in predictable ways. Too thin, and they evaporated before covering the fire. Too thick, and they couldn't flow fast enough to reach spreading flames. Some foams reacted with seawater, losing effectiveness the moment they hit a wet deck. Others broke down under heat, turning into useless liquid within seconds. Engineers tested dozens of variations. They burned fuel in controlled environments, measuring foam performance against stopwatches. They simulated carrier conditions, vibration, heat, cold, contamination. They calculated expansion ratios, drainage times, heat resistance thresholds. Every test generated data. Every failure pointed toward adjustments. But data alone wasn't enough. The foam had to be manufactured, stored, transported, and deployed by sailors who weren't chemists. It had to remain stable for months in storage tanks exposed to temperature extremes. It had to flow through pumps and hoses and nozzles that might be damaged, corroded, or improperly maintained. And it had to work the first time, every time, because there were no second chances when fire broke out at sea. The concentrate itself was mysterious to most crew members. It arrived in sealed drums, thick and viscous, labeled with warnings and mixing ratios. Diluted with seawater, it transformed into something that looked harmless but carried the power to stop disasters. Sailors who handled it developed a cautious respect. Spill it on your skin, and you'd spend an hour scrubbing. Breathe too much of the mist and your lungs would ache for days. But spray it on burning fuel and you'd watch flames die like candles snuffed by wind. Training became critical. Damage control teams practiced foam deployment in simulated fires, learning to judge coverage patterns, adjust pressure, coordinate with firefighting crews. Officers memorized activation sequences. Mechanics learned to maintain pumps and valves that might sit idle for months, then need to operate perfectly in seconds. And always in the background, engineers refined the formula. They tested new surfactants. They adjusted pH levels. They experimented with additives that extended foam life without compromising expansion rates. The work was incremental, unglamorous, invisible to the men fighting the war above. But each improvement meant more coverage, faster response, better survival rates. The foam system's real genius wasn't in any single component. It was in the integration. Tanks positioned for optimal weight distribution, pumps sized for rapid deployment, nozzles placed to cover maximum deck area. Everything was calculated, tested, adjusted. Nothing was left to chance. Yet chance still ruled the ocean. Equipment failed. Operators made mistakes. Combat conditions created scenarios no engineer had anticipated. And in those moments, the difference between survival and catastrophe often came down to whether one sailor remembered his training, whether one valve opened when it should, whether one chemical mixture performed as designed. The data from successful foam deployments began accumulating. Each incident report added knowledge. Each near disaster revealed weak points. Engineers compiled the information, adjusted protocols, issued new guidelines. The foam systems evolved not from theory alone, but from the hard lessons learned on burning decks across the Pacific. And slowly, reluctantly, the skeptics became believers, because the evidence was undeniable. Ships that would have burned now survived. Crews that would have died now lived. Foam wasn't a perfect solution. No solution was perfect in war, but it was effective, reliable, and increasingly essential to carrier operations. The chemistry of survival, it turned out, wasn't written in textbooks. It was written in fire and salt water, and the desperate calculations of men who refused to accept that burning fuel meant inevitable death. Chapter 4. The Sound Before the Fire. Veterans of carrier operations learned to hear disaster before they saw it. The change in engine pitch when a damaged aircraft struggled to maintain altitude. The scrape of metal when landing gear collapsed. The sudden silence when a propeller stopped spinning at the wrong moment. These sounds became warnings, triggering responses honed by repetition and fear. But the worst sound wasn't mechanical. It was human. the collective intake of breath from every man on deck when something went catastrophically wrong. That moment of recognition, before the shouting and the alarms and the chaos, when everyone understood simultaneously that death had arrived uninvited. Fuel leaks announced themselves through smell. Aviation gasoline had a distinctive odor, sharp and chemical, that cut through the salt air and engine exhaust. Deck crews learned to track it, following their noses to find damaged fuel lines or overfilled tanks or ruptured bladders. A small leak was manageable. A large one was terrifying. The protocols were clear. Identify the leak, stop the flow, clear the area, ventilate the space. But protocols assumed time and control, and carrier operations offered neither. Aircraft had to land whether fuel was leaking or not. Missions had to launch on schedule. The war didn't pause for maintenance or caution. Sailors developed instincts that kept them alive. They learned which parts of the deck to avoid when aircraft were taxiing. They memorized the locations of fire stations and foam nozzles. They watched the fuel handlers, reading body language for signs of trouble. And they carried in their minds a constant calculation, how far they'd need to run if something ignited. The foam system changed those calculations. Before foam, a major fuel fire meant evacuating the deck, sealing compartments, and hoping the firefighting teams could control the blaze before it reached ordnance or spread below decks. After foam, there was a chance, not a guarantee, but a chance, that the fire could be stopped where it started. Training drills emphasized speed. From the moment fuel ignited to the moment foam covered the flames, every second mattered. The operators practiced activation sequences until they could execute them blind. Damage control teams rehearsed response patterns, coordinating movements, establishing clear zones of responsibility. But drills couldn't replicate the psychological impact of real fire, the heat that made breathing painful from 20 feet away, the smoke that turned day into twilight, the knowledge that fuel tanks beneath the deck held enough gasoline to destroy the ship several times over. These factors transformed trained sailors into frightened men making desperate decisions. The foam operators bore a particular burden. Their stations were exposed, vulnerable, close enough to the action to see everything that could go wrong. They had to maintain focus while flames roared and men screamed, and the entire ship seemed to be dissolving into chaos. One wrong decision, activating too early, too late in the wrong section, could cost lives. Some operators froze. The human mind, confronted with overwhelming threat, sometimes simply stopped functioning. Training helped, but couldn't eliminate the possibility. Officers learned to identify sailors whose temperament suited the foam operator role. Calm under pressure, decisive, capable of ignoring their own fear long enough to pull the lever. Others proved themselves unexpectedly. Quiet sailors who seemed unremarkable during routine operations transformed into steady hands when disaster struck. The crisis revealed something in them that peacetime never demanded, a capacity to act when action seemed impossible. The sound that followed foam deployment was distinct. The rush of pressurized mixture through pipes, the hiss as foam met flame, the change in air pressure as oxygen was denied to fire, and then, if everything worked, a kind of muffled quiet as the inferno died beneath a white blanket. But success didn't erase memory. Sailors who survived fuel fires carried the experience in their bodies. The smell of burning gasoline triggered involuntary reactions months later. The sound of an engine backfiring caused them to flinch. Sleep came difficult when every nightmare featured flames and smoke in the faces of men who didn't escape. The psychological cost of carrier operations was rarely discussed. Men were expected to function despite fear, to perform their duties regardless of what they'd witnessed, to maintain readiness even after watching friends burn. Foam systems couldn't address this burden. They could only reduce the frequency with which sailors faced it. Chapter 5. The engineering beneath the foam system visible on the flight deck represented only a fraction of the engineering required to make it function. Below, in the carrier's vast interior, a network of tanks, pumps, valves, and pipes formed an infrastructure as complex as the ship's propulsion system. Foam concentrate tanks occupied carefully chosen spaces, low in the ship for stability, accessible for refilling, protected from combat damage. The tanks themselves were engineered to withstand pressure changes, temperature extremes, and the corrosive nature of the concentrate. They required regular inspection, testing, and maintenance that competed with dozens of other essential tasks. Pumps capable of moving foam mixture at high pressure were mounted near the tanks. These weren't ordinary water pumps. The foam's chemical composition and viscosity demanded specialized equipment that could handle the substance without degrading it. The pumps had to start instantly, operate reliably under stress, and maintain consistent pressure across multiple nozzles simultaneously. The piping system snaked through compartments, following routes that balanced efficiency with survivability. Engineers designed redundancy into the network, multiple paths to critical areas, isolation valves that could seal damaged sections, emergency connections that allowed jury-rigged repairs. Every joint was welded, tested, inspected. Every valve was labeled, mapped, drilled into crew consciousness. Control systems centralized activation while allowing local override. The primary operator station on the flight deck could trigger foam deployment across any section of the ship, but individual stations also existed throughout the carrier, giving damage control teams the ability to respond to fires in specific areas without waiting for commands from above. This distributed control created complexity. Sailors needed to understand not just how to activate the system, but when, where, and in what sequence. Premature activation wasted precious foam concentrate. Delayed activation allowed fires to spread beyond containment. The judgment calls required split-second assessment of conditions that changed by the moment. Maintenance crews faced constant challenges. Salt air corroded fittings. Vibration loosened connections. Heat degraded seals. The foam concentrate itself could separate if not periodically mixed, requiring time-consuming agitation of the storage tanks. Equipment that sat idle too long risked failure when finally needed. Equipment used too frequently wore out faster than replacement parts could be supplied. The Navy's logistics system struggled to keep pace with foam system demands. Concentrate had to be manufactured, packaged, shipped across thousands of miles of ocean, and delivered to carriers operating in combat zones. Shortages were common. Rationing was necessary. Ships sometimes operated with partially filled tanks, gambling that they wouldn't face fires large enough to exhaust their limited supply. Engineers aboard each carrier became experts in improvisation. They fabricated replacement parts from available materials. They adapted civilian firefighting equipment to military specifications. They tested alternative foam formulas when standard concentrate wasn't available. The innovations were rarely documented, never officially approved, and absolutely essential to keeping the systems operational. The weight of the foam infrastructure was significant. Every tank, pump, pipe, and nozzle added tons to a ship already pushing the limits of its design. Naval architects calculated carefully, balancing fire suppression capability against speed, maneuverability, and stability. The trade-offs were uncomfortable but necessary. Some officers questioned whether the foam systems justified their cost. They pointed to the deck space consumed by nozzles, the crew hours spent on maintenance, the logistics burden of supplying concentrate. They argued that better firefighting training and traditional methods could achieve similar results with less complexity. The counter-argument was statistical. Ships with foam systems survived fires that would have destroyed ships without them. The data was clear, even if it lacked the drama of combat victories. Foam didn't win battles. It prevented losses. And in a war of attrition, preventing losses mattered as much as inflicting them. Below decks, where engineers worked, the foam system was understood as part of a larger philosophy: redundancy, preparation, and respect for the dangers inherent in carrier operations. The enemy could sink you with torpedoes or bombs, but you could sink yourself with carelessness, overconfidence, or inadequate protection against the hazards you created. The foam system represented an acknowledgement that carriers were dangerous to their own crews, that fuel and fire lived in uneasy proximity. That survival required constant vigilance, sophisticated engineering, and the willingness to invest resources in problems that might never occur. If this story has moved you, leave a like. It helps others discover how ingenuity and courage saved lives, even in the deadliest workplace of the war. Chapter 6. The Moment of Choice. The call came during evening operations, just as the sun touched the horizon and visibility began to fail. A torpedo bomber returning from a strike mission radioed that it was losing hydraulic pressure. The landing gear might not deploy fully. The arresting hook might not function. The pilot's voice was steady, professional, but everyone on deck understood what those problems meant. The landing signal officer cleared other aircraft from the pattern. Deck crews prepared the crash barriers. Medical teams moved to forward positions. And the foam system operator took his station watching the approaching aircraft, calculating distances, timing, probabilities. The bomber came in fast, Too fast, trailing smoke. The landing gear deployed partially, one wheel down, one stuck halfway. The pilot compensated, tried to level the approach, but the aircraft's damaged hydraulics made precise control impossible. It hit the deck hard, the stuck gear collapsing immediately, metal scraping across steel, sparks showering in all directions. The fuel tank ruptured. Aviation gasoline sprayed across the deck in a wide fan pattern, vaporizing in the heat of the engine, mixing with air in ratios that guaranteed ignition. The pilot scrambled from the cockpit. Deck crews ran toward the aircraft, then away, then froze, uncertain whether to try rescuing ordnance handlers trapped near the crash site. The foam operator's hand hovered over the activation lever. Every instinct screamed at him to pull it immediately, to flood the deck before fire started. But protocol was clear. Foam deployment near an active crash site could obscure visibility, making rescue operations more dangerous. The decision belonged to the deck officer. Seconds passed. The gasoline continued spreading. The pilot was clear, but 3 men were still near the wreckage, struggling with a damaged cart loaded with ordnance. If the fuel ignited, they'd be caught in the flames. If foam deployed now, they might lose their footing, drop the ordnance, trigger an explosion that would gut the ship. The deck officer's voice came through the operator's headset. Stand by on foam. Give them 10 seconds. 10 seconds felt like an hour. The operator watched fuel pool around the aircraft. He watched the 3 men straining against the cart, trying to drag it clear. He watched other crew members edging closer, ready to help, but held back by the fire danger. And he felt the weight of the lever under his hand, knowing that his delay might cost lives and his ship. 8 seconds. 9. The cart moved. The men stumbled, regained their footing, pulled harder. The ordnance shifted, balanced precariously, then settled. They were moving but slowly, too slowly. Then came the spark, metal on metal, a fragment of the landing gear dragging across the deck, the tiniest flash, insignificant in daylight but lethal in the presence of vaporized gasoline. The fuel ignited. Fire bloomed across 50 feet of deck instantly, a wall of flame that rose higher than a man, fed by fuel still draining from the ruptured tank. The 3 men near the cart were engulfed in light, their silhouettes visible for one terrible moment before the flames obscured everything. The foam operator pulled the lever. The system responded in less than 2 seconds. Foam erupted from nozzles positioned around the crash site, flowing toward the fire in thick streams. The white barrier hit the flames and pushed through them, smothering, suffocating, denying oxygen faster than combustion could consume it. The fire fought back. It surged upward, trying to burn above the foam layer. It spread outward, seeking fuel not yet covered. But the foam kept coming, relentless, expanding across the deck, covering the spilled gasoline, creating a barrier between fuel and air. Deck crews ran through the foam toward the 3 men. The heat was still intense, the smoke still thick, but the flames were dying. They found the first man collapsed near the cart, his clothing scorched but his body intact. The second had crawled 10 feet before collapsing. The third was still standing, disoriented, looking at his hands as if surprised they weren't burning. Medical teams reached them within 30 seconds. Burns, mostly second degree. Smoke inhalation. Shock, but alive. All 3 alive. The foam had smothered the fire before it could kill. The crashed aircraft sat in the middle of a white landscape, its shape distorted by foam, its danger neutralized. The fuel leak had stopped, the fire was out, and the deck was already being cleared for emergency landings of aircraft still in the air with nowhere else to go. The foam operator remained at his station, hand still on the lever, breathing hard. An officer approached and placed a hand on his shoulder. No words, just acknowledgement. The operator had waited as long as protocol allowed, then acted the instant the decision was made. His timing had been perfect. His judgment had saved lives. But in the operator's mind, questions lingered. What if he'd pulled the lever 5 seconds earlier? Could he have prevented the fire entirely? What if he'd waited 1 second longer? Would those 3 men have died because of his hesitation? The questions had no answers, only consequences. And the consequence of his action was that 3 sailors would see their families again, that a carrier would continue operations, that the war would continue without losing men to fire. Later, after the deck was cleared and operations resumed, the 3 rescued sailors found the foam operator and stood before him awkwardly, uncertain what to say. One of them managed, "You waited." It wasn't an accusation. It was recognition. The operator had followed protocol even when every instinct demanded immediate action. and his discipline had given them the chance to clear the danger zone before foam made the deck treacherous. The operator nodded, unable to speak, feeling the weight of what hadn't happened as much as what had. The foam had worked. The training had worked. The system had worked. But beneath that success was the knowledge that margins were thin, that seconds mattered, that the next fire might not end so well. Chapter 7. The Cost of Protection. The foam system's success created new problems that no engineer had anticipated. Ships began requesting larger tanks, more nozzles, redundant pumps, backup systems. The demand for foam concentrate exceeded production capacity. Supply chains struggled. Carriers waited weeks for resupply, operating with depleted reserves, gambling that combat wouldn't force them to expend foam they didn't have. Maintenance requirements multiplied. The systems needed constant attention: testing, cleaning, calibration. Valves corroded, pipes clogged, nozzles became misaligned. Each failure point required inspection, and inspection required taking equipment offline, and taking equipment offline meant reducing fire protection during vulnerable periods. Training consumed crew hours that officers wanted allocated elsewhere. New sailors needed to learn the system. Experienced sailors needed refresher courses. Everyone needed to practice until activation became automatic, but training time competed with combat operations, maintenance schedules, and simple exhaustion. The foam itself proved problematic in ways that hadn't appeared during testing. Its slipperiness made the deck dangerous after deployment. Aircraft couldn't land safely until the foam was cleared, and clearing took time. Precious time when aircraft were running low on fuel and had nowhere else to go. Several carriers developed cleaning procedures that used seawater hoses and squeegees, but the work was labor-intensive and slow. Disposal created environmental concerns that seemed insignificant during wartime, but troubled some engineers nonetheless. The foam concentrate contained chemicals that contaminated seawater. Massive deployments left residue that could persist for days. The long-term effects were unknown, unstudied, and considered irrelevant compared to the immediate need to prevent fires. Some crew members developed respiratory problems from foam exposure. The mist created during deployment irritated lungs, especially in enclosed spaces. Sailors working in foam-covered areas complained of skin rashes, eye irritation, and persistent coughing. Medical officers documented the complaints but had no solutions. The foam was necessary. Its side effects were the cost of its effectiveness. Financial expense became a point of bureaucratic contention. The Navy's budget office questioned whether foam systems delivered sufficient value to justify their cost. They compared expenditures on foam infrastructure to expenditures on additional aircraft, ammunition, or crew training. The calculations showed foam systems consuming resources that could have been deployed elsewhere. But the calculations couldn't capture the value of lives saved or ships preserved. How do you quantify a fire that never reached catastrophic proportions? How do you measure the worth of sailors who survived to fight again? The numbers failed to reflect reality. And reality was that carriers with foam systems survived fires that destroyed carriers without them. Officers who had witnessed major fires became the foam system's strongest advocates. They testified before procurement boards, submitted detailed reports, lobbied for expanded production. Their arguments weren't theoretical. They spoke from experience, from watching men burn, from evacuating compartments, from feeling their ships shudder as fuel-fed fires consumed them from within. Yet skepticism persisted. Some commanders viewed foam systems as unnecessary complexity, an engineering solution to a problem that discipline and training could prevent. They pointed to carriers that operated safely without foam, to crews that managed fires using traditional methods, to the long history of naval firefighting that had served adequately for decades. The debate reflected deeper tensions within the Navy. Traditionalists resisted innovation that challenged established practices. Modernizers pushed for any technology that improved survivability. The foam system became a proxy for larger arguments about naval doctrine, resource allocation, and the nature of warfare itself. Engineers caught in the middle continued refining the technology. They developed lighter tanks, more efficient pumps, faster-acting formulas. They published guidelines for optimal deployment, maintenance schedules, and training protocols. They collected data from every incident, building an evidence base that gradually overwhelmed objections. By late 1944, foam systems were standard on all new carriers and being retrofitted onto older ones. The decision wasn't unanimous or enthusiastic. It was pragmatic. an acknowledgement that carrier operations were inherently dangerous, and that every available tool for reducing that danger should be employed. The cost was significant, in resources, in crew hours, in deck space, in complexity. But the alternative cost, measured in ships lost and sailors killed by preventable fires, was higher. And so the Navy accepted the burden, integrated foam systems into doctrine, and moved forward with technology that saved lives at the expense of simplicity. The irony wasn't lost on anyone. Carriers were designed to project power, to launch aircraft, to strike enemy targets hundreds of miles away. But their survival often depended not on offensive capability, but on the mundane effectiveness of firefighting foam deployed by sailors whose names would never appear in history books.